Hey y'all, it's Mr. Boyden back at it again today, and today we're going to talk about the unit circle. The unit circle really sets up the whole second semester of pre-calculus, and it's sort of like the quintessential pre-calculus topic where we start getting into trigonometry. Before we get into what the unit circle is and what we're going to do with it, let's check out some prerequisite skills. So I've got two questions here on the screen. I'd like you to pause the video and try them. These are going to be skills that are going to be important. You're going to have to be able to find these variables using what you learn in geometry if this lesson is going to make a whole lot of sense. So pause the video now and try them. Okay. In this first one, what we're going to notice is that we have the adjacent side and the hypotenuse. We need to remember that's cosine. Okay, so what do we have? We have cosine of 53 degrees equals the adjacent side 45 over the hypotenuse k. Okay, now I'm actually going to show the step on this one because it might be review. So we're going to multiply both sides by k to cancel that out. We're going to divide both sides by cosine 53. Divide by cosine 53. And then this would be known as calculator time. So here we go. So 45 divided by cosine 53. And I get 74, let's round it, 74.8. Okay, the one on the right's a little different. In fact, we have lots of options. In fact, since this is a Pythagorean triple where we have three whole numbers that make this right triangle, we can actually use whatever we want. I'm going to use tangent on this one. I don't know why, I just picked it. So tangent of alpha, that symbol is alpha, by the way. Kind of looks like a fishy. Tangent is opposite over hypotenuse. That would be 8 over 15. And all you need to remember is that when you type this in a calculator, it's the tan inverse button because we need to cancel out that tangent and find the angle. Okay, so 8 over 15 is what I'm going to use, and I get that that's 28.1 degrees. So alpha equals 21 or 28, excuse me, 28.1 degrees. Okay, so that's where we start today. Now let's get into the unit circle. By the time we're done today, you will know every single value on this diagram, and you'll know how to derive it, and you'll know where it comes from and why it is what it is. Pretty cool, huh? Might be kind of a longer video today, so let's get right into it. Okay, so first of all, what is a unit circle? Okay, because all a unit circle means is that it's a circle with a radius of 1. Okay, and the reason we start out with that is because if we understand the relationships on a circle with a radius of 1, we can then scale that up or down to any size circle we want. It's just that the math is easiest to think about when we start at 1. So, for example, if we then went to a circle, not to scale obviously, with a radius of 2, whatever length this was, if we compared it, they'd just be double. Whatever these coordinates are, they'd just be double because it's twice as big. If it was 1/2, then it would be half. So we start with a unit circle. We do need to remember how many degrees or radians are in a full circle, so 360 degrees and 2 pi radians. So with that, let's start thinking about what the unit circle is. Now, some teachers will have you just write down all the values. And so like literally just take a picture like this and start writing down all those values and try to memorize them. That for me is not real effective. So what I'm going to do is I'm going to show you that actually there's two different circles going on here. And so we're going to try to understand those. So to start, let's think about this scenario. A scenario in which we think of one big circle and we're going to have a group of 8 friends and we want to make sure everybody gets a slice of pizza of equal size. So here's where we're going to start. We're going to start by remembering, yeah, the circle has 360 degrees. So I'm actually, and I think I'll zoom in so it's easier to write and easier for you to see, just keeping in mind that we're going to have 8 friends here. I'm going to start by labeling the numbers of degrees. Now, y'all, you got to know that we start at 0 degrees over here on the right, and then it goes counterclockwise, okay? It's the exact same thing as the quadrants. So that's 0. This is 90, which means halfway in between that is 45, and I should maybe denote these as degrees. And then we keep going. This is 180, 270, which means we need to get all these numbers in between. So that would be 135. Okay, and if we have 180 and 270, right here we're going to have 225. It's just going up by 45 degrees. Notice each slice is 45 degrees. So then we would have 270 there, 315, and 0 would be the same thing as 360. So that can be a little weird for somebody to go, wait a minute, 0 and 360 aren't the same number. True fact. But the deal is, guys, we're not saying they're the same number. We're saying they represent the same location on the circle. They represent this point right here. Okay, and so the next thing that we want to do is now we want to convert all of these into radians. So while this is 0 and 360, it also is 2 pi. Remember, 2 pi radians is a whole circle. So if a whole circle is 2 pi, that means that half a circle must be pi. And so I'm just going to work my way down. So half of that would be pi over 2. And half of that would be pi over 4. So what that tells us is that each angle, each central angle in here is a size pi over 4. So rather than having you memorize all these different numbers, if you can remember that each slice is 45 degrees or pi over 4, then we can just add up as we go. So that was pi over 4, 2 pi over 4, which would make this 3 pi over 4, 4 pi over 4. Guys, notice 4 pi over 4. The 4s would cancel and it's pi. So keep counting. This is 5 pi over 4. 6 pi over 4. 6 over 4 goes to 3 over 2. So that's 3 pi over 2. So what will be 5, 6, 7 pi over 4. And then finally over here we'd have 8 pi over 4. 8 over 4 is 2. Okay, so now we have all of these locations described as angles, both in degrees and in radians. So now that we have that, we need to get the coordinates of all these points. So some of them are pretty easy. This one over here is pretty easy. You guys notice one thing that I haven't made clear yet, this right here is actually the y-axis on a graph, and this here is actually the x-axis on a graph, and we said that our radii are all 1. So if the radius is 1, and that's the origin, like that O for the origin, and we're going 1 to the right, right over here we have the coordinates 1, 0. What about out here? This one is up 1, so that's 0, 1. Over here, -1, 0, because we're going to the left, and down here, 0, -1. Now, what's going to be a little more interesting is finding the coordinates of a point like this one. So what I'm going to do is I'm going to draw in a triangle right here, and I hope you can see that triangle. I'm going to sketch that triangle again over here, and it's not going to be to scale, it's just how I sketch. Okay, and so I know that right here that's 45 degrees. And I'm going to use degrees just because a lot of you, I'm guessing, are more comfortable with degrees as of the day you're watching this video. And so what do we know? We know that right here the radius is 1, and if we knew what these were, y and x, if we knew those, then we would know the coordinates of this point. So if I wanted to, I could go into the calculator and do a sine equation and a cosine equation, type those in, and we would get those values. But the problem is they'd be decimal approximations. So here's what I'm going to do. I'm going to notice that since this is a 45, 45, 90 triangle, that means it's isosceles, which means these two lengths are the same. So now I can use the Pythagorean equation. X squared plus x squared equals 1 squared, which is pretty easy to simplify down to 2x squared equals 1. Let's divide by 2, so x squared equals 1/2, and then we're going to need to take a square root of both sides. So x equals plus or minus the square root of 1/2. Now, functionally there's nothing wrong with leaving it as this, but what we're going to do, we're going to simplify that radical. So that would become x equals plus or minus 1 over root 2, and then we're not allowed to leave irrational denominators, so we're going to rationalize it like this. And so what do I get? X equals plus or minus root 2 over 2. So what we just showed is that this length right here is root 2 over 2, and this length right here is also root 2 over 2. And since this triangle I drew up here is the exact same triangle on my diagram, that now tells us that the coordinates of this point are root 2 over 2, comma, root 2 over 2. Now we have those coordinates. So I used to think that all of these points were distinct, and I'd have to redo the calculation every single time. But I hope that you notice that over here, when I draw in the triangle, you see how that's the same exact triangle as this one? Or this point and this point are actually the same point, just reflected across the y-axis? Well, if you go back to Unit 1, we learned that when you reflect something across the y-axis, that just makes the x-coordinate the opposite. So over here, the coordinate is negative root 2 over 2, comma, root 2 over 2. What about down here? That's the same point reflected across the x-axis. So now the y value becomes negative. So down here we have the coordinate negative root 2 over 2, comma, negative root 2 over 2. And then over here on the right, we've just reflected that point to the right again. So now over here we have the coordinates root 2 over 2, comma, negative root 2 over 2. And so with this pizza, where we have our 8 friends, we've been able to, with one little calculation, find the coordinates of all of these locations. So that's this case. Now let's consider the case if we have 12 friends. In this case, 12 friends, we want to make sure everyone gets a slice of equal size. First thing I want you to remember, y'all, this is the exact same pizza as before. Okay, its radius is still 1. This vertical line is still the y-axis, and this horizontal line is still the x-axis. Okay, the only difference is now we've cut it up into more pieces than before. So I'm going to zoom in here again, and my intention with this drawing is that all the slices were of equal size. It looks like they're off by just a little bit, but pretend or make the assumption as we go through this that they're all of equal size, okay? So we're going to start the same way we did last time, with 0 right here, with 180 right here, with 90 right here, and with 270 down here. Now, notice this is 90 degrees over here, which got chopped into 3 bits. So this is 30 degrees, and 30 more gets me to 60 degrees. Let's keep counting. 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330. Now, guys, truth be told, the only reason I'm putting degrees on here is so it's easier for you to understand it. After today, we're really not going to refer to degrees much anymore. We're really going to make a switch to radians. And that might sound scary at first. It actually, my experience was, yeah, at first it was scary, but after a little bit, it's actually way easier and more intuitive. Okay, so now that we have that, let's go back and put in radians. If that's pi, or excuse me, 2 pi is a full circle, then we already know that half a circle is pi. And we have pi over 2 up here, or half pi. And so what do we have down here? Okay, this is 1/3 of pi over 2, so this is actually pi over 6. So what we can now say is that each of these slices has a central angle of 30 degrees, which is the same as pi over 6. Now what I do, rather than trying to do all kinds of addition and division and all kinds of weird stuff, what I do is I just go around the circle to each spot the same way we added 30 with the degrees. I just had pi over 6. So I got pi over 6, the next one's 2 pi over 6. Okay, hold on, 2 pi over 6. 2 pi over 6 is the same as pi over 3. So degrees, 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 degrees. All right, so we had 2 pi over 6. The next one's 3 pi over 6, which is pi over 2. We already had that. So pi, 2 pi, 3 pi, 4 pi over 6. Okay, hold on. 4 pi over 6. That reduces to 2 pi over 3. Then 5 pi over 6. 6 pi over 6. 6 over 6 is pi. 7 pi over 6. That doesn't simplify. Okay, 7 pi over 6, or let's redo that. That's a little sloppy. Whoops. All right, that's better. 7 pi over 6. I want to practice vertical fractions. Okay, 7 pi over 6, 8 pi over 6. That simplifies to 4 pi over 3. Okay, 4 pi over 3, so 7 pi over 6, 8 pi over 6, 9 pi over 6, that simplifies to 3 pi over 2, which is exactly what we had on the other pizza. 7, 8, 9, 10 pi over 6, so that simplifies to 5 pi over 3. We had, what, 7, 8, 9, 10, 11 pi over 6. And then we'll double check this last one. That would be 12 pi over 6. And 12 pi over 6, 12 over 6 is 2. So that all lines up. All right, so we have all of those descriptions in radians. I'm going to go back and get rid of the sort of side work because I'm going to need that space here in just a second. Now we want to begin to work on finding coordinates. Now the first one at 0 degrees and at 90 degrees, those are the same as before. Okay, so this is still 0, 1. And this over here is still 1, 0, but we may need to do a little bit of extra work to find the coordinates right here. So again, I'm going to notice that location, remembering that I have a radius of 1. I'm going to draw in that triangle. Okay, now one of the things that jumps out at me about this triangle as compared to the previous one, I know my drawing looks the same, but it's not isosceles. The side lengths are different. So I've got 30 degrees there, and then I've got, what, a radius of 1. Okay, and so I've got some y value and an x value. Last time I was able to change that to x because it was isosceles, but this time I need to leave it as y because they're not the same. So guys, there's a lot of different ways you can think about this. One of the ways that I'm going to do today, because I find it most intuitive, is I'm actually going to make one bigger triangle here. So I'm going to incorporate this location right here. And what I'd like you to see is now I have one bigger triangle. Okay, it goes all the way like this, and you don't need to sketch this part in necessarily. I'm just showing you where all the coordinates come from, okay? And so that's a 1, and that's a 1, and one thing that jumps out at me here, if that's 30 and 30, this is a 60-degree angle, and if it's isosceles, these are 2, so I've actually made an equilateral triangle now. And so perhaps that's going to be easier to use to think about this. I'm going to draw that part in here. And so that's 1, and that means that this is also 1. Now guys, it should be fairly intuitive for you right now to identify what y is. Okay, we just showed that if I have 1, 1, and 1, this is y, and since those are congruent triangles, that's also y. So that would tell us that y equals 1/2. And if y equals 1/2, which it does, then what I have here now, I have a triangle which is a right triangle, and I know 2 sides, and I want to know the third, so I can use the Pythagorean theorem. So that's going to be 1/2 squared, I'm going to switch back to a darker color so it's easier to see, plus x squared equals 1 squared. Let's do the math. Okay, 1/2 squared is 1/4, plus x squared equals 1. Let's subtract 1/4 on both sides, so we get x squared equals 3/4, and then we'll take the square root of both sides, so we get the square root, or plus or minus, the square root of 3 divided by 2. Now notice where that fraction bar is, guys. I've actually taken the square root of 4 to get the 2. So I have root 3 over 2, and that's what x is. So I now know x, and I know y, which means I know these coordinates. Cool. So what I have is my x value, root 3 over 2, and my y value of 1/2. Okay. Now, what I like to do is recognize that every triangle on this particular pizza, because all the slices were congruent, all the triangles are the same. So if I draw to this location in this way, can you see how this triangle is congruent to the original triangle we had? Which means it must have the same coordinates, it's just that it's been moved up here. So the only difference for this one is that now the x value is 1/2, and the y value is root 3 over 2. Now that might be a little bit confusing to understand that. Here's what I want you to notice though. The shorter side of this triangle is always 1/2. The longer side of the triangle is always root 3 over 2. And guys, if you're not sure, root 3 over 2 is a little bit bigger than 1/2, and that's a way you can keep it straight because the square root of 3 is a bigger number than 1. And so looking at this triangle up here, I hope you can see that the x value is smaller than the y value on this triangle. The horizontal is shorter than the vertical, which means the horizontal must be the smaller number, which is 1/2. Okay, now we already knew the coordinates here. We wrote that down. Now we're going to keep going. And so now that we get this basic relationship, we actually don't have to do the calculation again. So I'm going to come over here. I'm going to zoom these in a little bit so it's a little bit easier for me to write, and hopefully it'll be more legible for you. Okay, over here, I'm going to draw my triangle, and it looks like the short side of my triangle is going from the origin. It's going to the left, so that's negative 1/2, and it went up, so root 3 over 2 are my coordinates right there. What about down here? I always draw on the triangle. Okay, it looks like the longer side is the x side now, and it's going to the left, so that'd be negative root 3 over 2. It's going up, and that's the short side, so 1/2. Okay, what about over here? We'll keep going. Okay, this time it looks like I'm going down, and we're in quadrant 3, so both the x and the y values are going to be negative now. Looks like the longer one is the x, so that would be negative root 3 over 2, comma negative 1/2. Down here it's just going to be flipped. Okay, if you notice, these two will always just be flipped. So what do we have? We have negative 1/2 and negative root 3 over 2. What about down here? Hey, that's an easy one. So that's 0, comma negative 1, because that's just straight down, no left and right. I'm going to shift the diagram here. And so what do we have here? We've got our triangle. I'm going to sketch that in. Looks like the short side is the x value. So that would be 1/2, comma, negative root 3 over 2. And then over here, that one we kind of already did. Okay, so it's root 3 over 2 going to the right, comma, negative 1/2. All right, so we now have our two pizzas all chopped up. We know all those coordinates. And this is going to represent all of the patterns on the full unit circle. So guys, again, it's a lot easier if you break this down into two different scenarios rather than one. It's a lot easier to see the patterns. So like how we counted pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Or recognizing that, hey, guys, look, in the corners, so all the way to the right, left, up, and down, the only numbers for the coordinates were 0 and 1. And then in all of the other locations, the only options for the coordinates were root 3 over 2 and 1 over 2. That's it. It's just all you have to decide is which one is x, which one is y, and are either of them negative or not. Okay, so that should make it a little bit easier. Very similar pattern on the previous one. Okay, notice there's only, well, actually there's only one number. It's root 2 over 2 all the way around. So anytime it's one of these multiples of 4, it's going to be a root 2 over 2 and a root 2 over 2. So let's go back to the original drawing that I said you'd understand by the time we were done. Okay, so here it is. There's a couple of patterns that I want to point out to you so this is easier to understand, because the first time I saw this, it looked like just total chaos to me. I want you to realize, as far as the coordinates, there's only a few numbers that pop up. 0, 1, 1/2, root 2 over 2, and root 3 over 2. Those are the only 5 numbers for coordinates. And you might realize these two are always paired together. Look, they're always paired together. These two are always paired together. 1/2 always comes with root 3 over 2. It's not ever going to come with anything else. So that eliminates a lot of ways to get these types of understandings wrong. And then root 2 over 2 always dances with itself. Okay, it always comes partnered with itself. We can see those examples here in red. And that's why they're in a different color, because they represent a different kind of relationship. So notice here, everything in black is the 1-0 combination. Everything in red is the root 2 over 2 combination. And notice, they all have a 4 in their denominator. 4, 4, 4, 4. And that's one reason that it might be easier to use radians than degrees, is because we can notice patterns like that, whereas it's harder to think of it as being multiples of 45 for degrees. And what about these in blue? Okay, those are the ones with the 1 over 2 and the root 3 over 2. Notice, what do they have? They're always over a multiple of 3. 3, 6. 3, 6. 6, 3, 3, 6. Okay, and so we can kind of pair those up, and that will make it easier to understand.